Hi, I'm Jun. I'm a PhD candidate at Indiana University, Purdue University, Indianapolis. My advisor is Professor Hassan. Today, I'm going to introduce our work, Robust Node Classification on Graphs, Johnny from BayesianLabel Transition and Topology-based Label Propagation. In the beginning, I want to introduce the background. Node classification is a common graph machine learning task that trains a model to learn in which class a node belongs. In recent years, graph neural networks are widely used in this task. However, the performance of graph neural network may be weakened when the graph structure is substantially changed. We analyzed 3 scenarios in this study and summarized them as a topological perturbation. For example, the first case is random connection by selfish user for business purpose in online social network. The second case is that the message passing mechanism of graph neural network performs poorly on nodes with sparse connections. The third case is adversarial attacks. In this work, we aim to improve the robustness of the graph neural network against topological perturbations. In this work, we select graph convolutional network as the backbone graph neural network. Here we present how graph convolutional network aggregates the nodes in each layer and its loss function. Recent studies tackled the perturbation issues by Bayesian-label transition. These methods recover the performance by post-processing the predictions. However, label transition suffers slow convergence as the posterior distribution from which the Gibbs sampling samples the node label adapt incrementally over a sequence of label propagation, followed by graph neural network retraining iterations. Slow convergence leads to inferior performance because the label on which the graph neural network is retrained may not be accurate, as the Bayesian-label transition may have not yet been converged. In this work, we propose a new label inference mechanism that can infer node labels, jointly from label transition and propagation. Our model can converge faster than the Bayesian-label transition using Gibbs sampling. We release the constraint of symmetric Dirichlet distribution on the Bayesian-label transition and verify that dynamically updated Dirichlet prior can help better label inference. Extensive experiments demonstrate that our model achieves robust node classification on 3 topological perturbation scenarios and outperform 8 popular defending models across 5 public graph datasets. Before introducing our model, we first formally state the problem. Given a graph and manual annotated labels, which are used for training a GNN-based node classifier on unperturbed graphs, we aim to develop a label inference model to improve the robustness of the node classifier on perturbed graphs by approximating the inferred label to the latent label as identical as possible. Next, we introduce the basic idea of Bayesian-label transition by the plane diagram. This diagram presents the dependency of the variables. V denotes the nodes. Z denotes the unobserved latent labels. Y denotes the observed noisy labels. Phi denotes the transition metric. It has a parameter alpha. The dependency can be formulated as follows. We further explain Bayesian-label transition via a toy example here. We assume the latent label are unobserved and the noisy label are observed. In this example, we can see the node C is noisy labeled as the yellow color. Let's say the perturbator connects the node C and the node D. Now node D is turned into yellow colored. This is the transition metric between noise label and the predicted labels for 3 classes. After applying label transition, we approximate the inferred label to the latent label as identical as possible. In this slide, we will go through the pseudocode of our proposed model. In the input, both train graph and the test graph contains corresponding symmetric, adjacent symmetric, and feature metric, but only the train graph contains manual annotated label YM. We first train the node classifier with YM on the train graph. Then we generate initial categorical distribution and auto-generated labels YA. We also need to compute the warm-up transition metric based on the train graph and define infer labels, dynamic transition metric, and initial alpha vector. Here, we tune the initial alpha value in the validation set. For each transition, if the transition is in the warm-up stage, we sample the label with the warm-up transition metric by our proposed sampling method. After the warm-up stage, we use the dynamic transition metric instead. In each transition, we will update the alpha vector, dynamic transition metric, and also retrain the node classifier to update the categorical distribution for the next sampling. At the end, we got the infer labels. This is our first contribution. We use a toy example to explain the motivation of using a symmetric Dirichlet distribution. The leftmost triangle is a symmetric Dirichlet distribution with alpha value 1. All instants follow uniform distribution. The middle triangle has equal alpha value 0.1. At this point, instants tend to move to the corners. The rightmost triangle has different alpha value. We can see that an instant has higher probability to be assigned to a class with higher alpha value. This intuition motivates us to use different initial alpha value and dynamically update the values as the number of instances changes. The proposed new sampling method is the most important contribution in our work. In one iteration, given a categorical distribution, transition metric, and a topology-based label sampler, we traverse each node and sample a label ZI. We will update this label with the given sampler if this label is uncertain. Here we define a label is uncertain such that this label is inconsistent to its previous invert label or the auto-generated label in this node. Here we further explain our sampling method with a toy example. The left-hand side is a transition metric. Let's say we first infer a label of node A as red because of the highest probability. Then we will apply label propagation on this node if the node label is uncertain. The right-hand side figure shows that most neighbors of node A is blue, and we will assign the blue as the class of node A. In this work, we propose 3 types of topology-based label samplers. The first one is random sampler. It randomly samples a label from the neighbors. The second one is majority sampler. It samples a label from the majority of the neighbors. In this example, red color has 3 nodes nearby the node C. Then we assign node C into the red class. The third one is degree weighted sampler. It samples a label based on the weighted degree of the neighbors. In this example, red class has the highest weight, so that we assign node C into the red class. We have 2 conjectures to analyze convergency. First, given large enough iterations of transition, the transition of infer label will eventually converge. Second, our proposed method helps the inference converge with fewer iterations of transition than the Bayesian-based sampling. In the experiments, we will verify these 2 conjectures. The slide presents the experimental settings such as dataset, competing methods, evaluation metric, and the type of perturbations. Here we use accuracy and normalized entropy to evaluate the performance of our model. Here we list the statistics of our datasets. The last column shows that the edge homophily ratio, because this is one of our assumptions of label propagation. This experiment examined our model on top of GCN under 3 scenarios of topological perturbations across 5 datasets. In this slide, we present the result under random perturbations. The first row is the originally performance on Proto graph. The second row is the baseline model. The third row is the vanilla architecture of our model. The last three rows present the result using different set as topology-based label sampler. The result shows that using topology-based label sampler can help recover the accuracy on Proto graphs and outperform the baseline model. We empirically analyze the convergence between our sampling method and Gibbs sampling. The result indicate that our method converge faster than the Gibbs sampling. This result presents the convergence from the perspective of the ratio of uncertain nodes. The ratio decreases faster using our sampling method. We compare the defending performance between our model and the competing methods under the random connections. The result shows that our model outperforms other competing methods. The initial alpha value is a crucial parameter for our model. We examine different initial value in this experiment. The result indicates that dynamically updating the alpha vector can help achieve higher and robust performance. However, our model has some limitation. First, using the topology-based sampler may fail to boost the classification accuracy on extreme sparse graph, where most links and features are sparse or missing. Our label inference model highly depends on an accurate price distribution. In other words, our model couldn't handle the poisoning attack. In the future, integrating a denoising approach on the price distribution would be a possible solution to mitigate this issue. Third, our model couldn't recover the missing class from the prior distribution. This limitation implies that our model currently cannot handle the open set classification. In the future, we could jointly utilize a distance-based label transition metric to detect potential unseen classes during the inference. Our model may contribute other research areas, such as the noisy labeling and the uncertainty estimation. On one hand, we train the GCM with noise labels for downstream inference. Our work could further contribute to this field as the BayesianLabel transition model may recover the no label distribution using noisy label with different noisy ratio. On the other hand, our experiments demonstrate that label inference can significantly decrease the uncertainty of node classifications. In conclusion, in this work, we aim to improve the robustness of a GNN-based node classifier against topological perturbations. To achieve this goal, we propose a new label inference model, namely LInDT, that integrates both BayesianLabel transition and topology-based label propagation. This abbreviation is similar to a chocolate brand name due to the saying, "Life is like a bar of chocolate. You may never know the favorites until you taste one." Label inference could be an analogy to this saying because we may not know which label will be eventually sampled until the inference is converged. Extensive experiments demonstrate the following conclusion. GNN-based node classification can benefit from our model until under three scenarios of topological perturbations. Our model converges faster, achieve higher accuracy on node classification while maintaining normalized entropy at a low level, and surpasses popular competing methods across 5 public graph datasets. Adopting a symmetric Dirichlet distribution as a prior can contribute to label inference. That's all. Thank you for your listening.